Okay. So what we are going to do today, we are going to start system of first order ODEs. Okay. System of first order ODEs. Okay. So you may be aware of the fact that, like say, an ODE, it may be linear or non-linear. Okay. So what we are going to do, let me give you a roadmap to what we are going to do. So firstly, I am going to consider the linear part. Okay. And from the linear part, I'm going to introduce you. In fact, I don't think you need any fresh introduction. Probably you have already done it before. Some of the basics, but I'm just going to show you the related theorems. I'm not going to prove it because most of them you have already done in your BSc and MSc days. Okay, and while still on linear, I'm going to consider different type of solutions. But at the beginning, I'm not going to visualize those solutions. You may be pondering why it is so, because in between, I'm going to move to nonlinear equations, and from there, I'm going to introduce you to the critical points, and depending upon the nature of the critical points, it is easier to visualize the solution of a system of first order ODEs, whether it is linear or non-linear. Okay, so once I am done with that, then I am going to go to your autonomous system. So I'm not sure whether autonomous system is going to come in between or just after that, and then just a little hint of dynamical system I'm going to give you. Okay, dynamical system. Okay, fine. So now, can anybody tell me, why we are so much interested in solving system of first order ODEs? Can anybody give me some kind of motivation, like say why we are studying this?
So higher order differential equation can be reduced to first order differential equations for suitable, then yes.
Under suitable transformations, okay, or under suitable redefinition of the variables, right? Okay, that can be one of the motivation. So what he is saying is that what you can do if you have an nth order differential equation, okay, of course, nth order ODE, what you can do through some suitable transformation or suitable redefinition, you can convert that single equation into a system of n equations, okay, n first order equation, because higher order equation, their solution is always difficult, right? So rather than that, if we are going to solve only a system of first order ODEs, then it is going to be much more simpler for us. But what I'm more interested in is that is one of the motivation. But my interest is in the dynamical system, okay? Because many of you are going to study the nature of your solution, as it evolves with time. That is where I am going to be more interested in. And you know that, whatever is happening in the world, if you want to mathematically model it, you are going to model it in terms of space and time, okay? So basically, you are going to have maximum 3 space variables, x, y, and z, and time variable t. Okay, so how x, y, and z they evolve with respect to time, I'll be more interested in them. Okay, or for that matter, if you consider some function of the space variables and time variables, okay, so that function, how it evolves with respect to time, that is where we are going to be more interested in. Okay, so to begin with, let me show you a cute little picture here. Okay, what do you see here? Can you tell me what are they?
One is rabbit.
Yes. And the other one looks like a dog, right?
Yes, sir.
It looks like a dog, but I mean, in fact, it's not a dog. I'd say baby fox. In fact, that rabbit is also a baby rabbit. That's why both of them are there being so cute, right? But as I have told you, I'm going to be more concerned about some variables which are dependent variable, which are functions of independent variable x, y, z, and t, right? Now, these two little cuties, they over time, they no longer remain, I mean, frames. As you can see here, like, I mean, when they grow older, what you can see here. In your previous picture, the baby fox, I mean, its size was, right, smaller than the baby rabbit, right? Now what is happening? Can you see what is happening? It's a very straightforward picture, right?
Yes, sir. Yes.
What is happening here? A fox is running away, an adult rabbit, right, in his mouth. Okay, fine. Okay then. So that is good enough. That is good enough. Okay. I'll come back to this again. And I will show you this slide. So that has given you some idea. So what we'll be interested in. Okay. So if you look carefully, or now because I have already switched off my slides. So if you think carefully, what happens there? I have fox, I have rabbit, right? And suppose they coexist in a particular region. They coexist in a particular region. And let us assume that the fox, they eat only the rabbits because they are carnivorous, and the rabbits definitely they are going to feed on some kind of this grass material. Okay, so grass type of I mean food. Okay, vegetable. Okay, so suppose that I mean grass is in abundance. Suppose grass is in abundance. Okay, so if I consider, say, suppose x PD variable representing the population of fox over time t. Similarly, y is the variable representing the population of rabbit over time t. Okay, so then what is going to happen? Like, say, the rate of change of the population of fox, it is going to be denoted by dxdt, right? dxdt. And suppose, I mean, there is no rabbit population. Suppose there is no rabbit population. Then what is going to happen? Because the foxes, they strive on eating the rabbits. Without rabbit being present there, their population is going to dwindle, right? Their population is going to decrease. Is it okay with everybody? Right?
Yes, sir.
Right?
Yes.
So that is why it is going to be something like say some constant say minus a into x, right? Where a is a positive constant. Right? Because again, their rate is going to depend upon their own population, right? How the population is increasing or decreasing, right? So I mean, there through mating, the population is going to increase, right? And again, because they are running out of food supply, so that is why the population is going to decrease, right? So everything is going to depend upon the population itself, but we know that it is going to give you a decreasing trend because there is no rabbit available. Fine, okay. So now let us see the second scenario. Let us see the second scenario where I am considering the population of rabbit in the absence of fox. Okay, suppose there is no fox, right? So that means the rabbit population, there is no one in that region, and I am simply assuming that in that particular region, in that particular territory, only fox and rabbit are present. Okay, there are no other animal or human beings. Okay, so then what is going to happen? Because no fox is there, right? The fox are nothing but their their predator, and rabbit is prey, right? And because there is no predator, that is why their population is going to increase in abundance. Is it okay with everybody? Because they have enough grass there to survive. Is it okay?
Yes, sir.
Fine?
Yes, sir.
So that is why in the absence of fox, this is going to be something like this. This is going to be something like this. Is it okay? Fine? Now, what is going to happen? Like, although these two are like, say, they are kind of absurd scenarios. This is not going to happen. There is always going to be coexistence of both the fox and rabbit population, right? So that means one population is dependent on the other, right? So that is why if I multiply x into y, that is going to show me what? That is going to show me the dependence of x in y, right? This is kind of this variable xy is kind of showing the dependence of the population of x in y and vice versa, right? And depending upon some factors, if both rabbit and fox populations are there, coexistence, so then what is going to happen? Obviously, in the presence of rabbit, because now the fox has something to eat, their population is going to increase, right? So what is going to happen? Their population is going to increase with some rate b, which is again dependent upon the population of the rabbit also, because more the number of rabbits are present, so more they will have food, right? So similarly, what is going to happen in the presence of fox population? The rabbit population is going to decrease. Again, as I have told you, they are interdependent, and since it is decreasing, I am going to have some positive constant d in such a way that this is what happens. Is it okay with everybody? See, here what I am trying to get, I am trying to get a very simple mathematical model. Is it okay for the time being? Fine?
Yes, sir. Yes, sir.
So here you can see that. I can write this as x into minus a plus by, and this is y c minus dx. Okay, right? So this is what is all about. This is what is all about your first order ODEs. This is where not only first order ODEs, but a system. This system consists of only two equations. Now you can see that through mathematical modeling, just by simple first order equations, first order ODEs, we can mathematically model a system. Of course, this is a very simple model, and this is called predator-prey model. Okay, fine. And what is going to happen? There is going to be interplay between the population of the rabbit and fox. So, depending upon the situation, and you know that both of them are coexisting. So I am going to have like something like this. I'm going to have, say, if this is fox population and if this is rabbit population. So I am going to have something like this. Okay. So definitely, if fox population increases, rabbit population is going to decrease. Now again, when rabbit population is going to decrease, then what is going to happen? The fox, they will be running short of food, right? And in that way, their population also will start decreasing. So once their population start decreasing, because the rabbits, now they are relatively free from, predator. That is why their population is going to flourish. So in that way, it is going to increase. So there is going to be increasing and decreasing trend throughout. Okay. So then the actual graph, it is going to look something like this, as you can see here, where my cursor is. Okay, where my cursor is. So here, like say, it depends on exactly at what time you have started. Here, the solid line represents the population of rabbit, and the dotted line it represents the population of foxes. And you can see that, they are showing, like say, initially it is decreasing, and then again it is increasing, and so on. Right? So basically, what I want to tell you here is that, say, this equation, it has given you an idea that these two equations, I can write it as something like your g of xy. Although here t is not explicitly present, but I can still roll that in. So, like, this is where the origin of a system of first order ODE come from. So, say I have given you just one of the motivations. There are many cases, which require the use of system of first order ODEs. Okay, fine. So now let me come to the mathematical part. Okay. So, So what I'm going to do, I'm going to give you the matrix equation, and after that, the theorems related to that, I'm just going to show you their statements in slides. Okay. Then I will start with different type of solutions of a system of homogeneous linear first order ODEs. Okay, fine. So now suppose your x1, x2 up to xn, suppose all of them are functions of the single variable t, right? And suppose it is defined in an interval a. So basically what we have, these xi's, they are nothing but functions from the closed interval, this set of real numbers r. Okay, fine. And then suppose I have a system of first order ODEs. It is given by say g1, x1, x2 up to xn t, and similarly dx2 dt, this is equal to g2 x1 x2 xn t, and finally say dxn dt, this is equal to gn x1 this t, right? Can you tell me what is the domain of these gi's? What is the domain of GI? Of course, here I goes from 1 to n. Yes?
Rn plus 1.
Rn plus. Any difference in opinion? I don't think there should be any difference of opinion, right? Because you know that the entries x1 up to xn, they belong to the set of real numbers. Okay, fine. Is it Rn plus 1 or I can further
Rn cross equals
Rn cross AB, right? Rn cross AB to R. If you want to be more precise, but roughly R and plus 1 to R is also fine. Okay, right. So this is my system of equations. So now see the way I have written this equation. If you look at the right hand side, I don't have any idea how the functions are going to behave, right? I don't exactly know what is the expression for those functions defined on the right hand side. Okay, so if you are given a system of first order ODEs like that, then you have to assume that in general, the right hand side, it is going to give you a nonlinear expression. Okay, because here the dependent variables are x1, x2 up to xn, right? And you know that they may appear what? Non-linearly, right? So that is going to make this system of equations as a system of non-linear equations. And now, can you tell me that those predator prey model, like say dx dt and dy dt, the way we have generated them, it was minus a plus dy, I think, and this is y c minus dx, right? So can you tell me whether I can consider them as linear or non-linear? Yes.
non-linear.
They're not linear. They're not linear. See, because these are x. This x into y, right? They are dependent variables, isn't it? Right? The product of dependent variable, it appears there, right? So if you consider the order x to the power 1, y to the power 1, it is going to be more than 1. So this is going to make it non-linear. Okay, fine. So now what I'm going to do, I will be interested in a system of linear first order ODEs. And you may be asking me why, why I am doing linear first order ODEs, or for that matter system of linear first order ODEs, whereas the mathematical model, I told you that it is one of the simplest mathematical model for predator prey, and that was non-linear, right? But like say the real life system, it is highly non-linear, but we are still studying or trying to study only linear system. Can you tell me why? Why linear? Any idea? Don't think too high. I want a very basic answer.
So linears are more simpler.
Linears are
more simpler to study.
Yeah, like say yes, that is the most honest and basic answer. See, in order to study some complicated system, what you will have to do, you'll have to go from the basics of the one of the most simpler forms. So, like basically, what is going to happen in your research also later on, you are going to see that on a single day, like even in 1 year after your research, you are not going to get your result, right? And you may be very much frustrated. You may be very much frustrated. But the thing is that you are only going to get delta x increment in your success. So this is also, it is like that. The linear system, they're nothing but the building blocks in order to study nonlinear system later on. And you will see that if you study advanced numerical analysis, or those who are going to be doing PhDs in some numerical methods or computational thing, you will see later on that there is some concept called linearization. Linearization. So what it does, it converts a system of, nonlinear equations into locally linear systems. Okay, and solve it, and eventually they prove that both the approaches, whether you go through the linearization or the purely nonlinear part, it is going to converge into the same result. Okay, fine. So that is why I will start with linear first. Okay. Okay. So now I will start with system of linear first order ODEs. Okay. And again, it may be a repetition for some of you, but still, I want to do a recap because, again, see what happened earlier. We were more interested in getting marks in our BSc or MSc exams without actually understanding some of the concepts, right? So now I want your knowledge to become okay. So as before, suppose I am considering n functions x1, x2 up to xn, right, in the interval a, b, and I'm assuming that t is my independent variable. Okay, so then if I consider a system of linear equations, so then I'm going to assume that I have something like this. Say, suppose this is say f1t. So similarly, dx2 dt. This is again a1 to t x1, a2 to t x2. Likewise, a2 1 t xn plus f to t, and finally, my say dxn dt. This is a 1n dx1 plus a 1 t x2 up to a n.
Sir, that will be n1 or 1n.
Which
the
one?
First, dx2 dt equals to a21.
Oh, this is, yeah, because I started with the first year. 2 1. So then this has to start with n1 and 2. Okay. Yeah, thank you. Okay. So then and here I'm assuming that all these a ij t, right? I'm assuming that they are continuous functions of t, okay, in the interval ab. So basically, I'm assuming that t lies in the interval ab, right? And of course, all these functions fit, they are also continuous in a. Okay, fine. So now, what we do here, we convert it into a matrix equation. So for that, what we do, we write this as a vector x1, x2 to xn. Say here I am putting a bar over here because in the books it is easier for you to understand that if it is written in boldface, it is a vector, right? I don't have that facility here, or I can make it bold, but it is going to take me a lot of effort. So from now onwards, you should know that whenever I am going to put a bar over a variable, so that is going to represent a vector here. Okay, fine. So then if I do this, and then if I write, say, f as f1t, f2t up to fn, okay, and then if I write a to be equal to a11t, a12t, a1nt, b21t, b22t, sorry, a21, a2nt, and finally an1t, an2t, an2t, fine, an&t. So then this system of equations, definitely you know that what I can do, I can write this as simply ddt of something like this. And even if I don't write it as f1t, f2t, fnt, etc., you should assume that if I simply write f1, f2 up to fn, you should assume that they are functions of t, right? So similarly here, a1 and t, then a1t, a2t, and finally a1t up to and right? I could have written it like this, isn't it? Right? So that is why this system of equations, it can be written as this. This is the matrix form of the equations. Okay. So now that has probably given you an idea. That whatever we are going to do later on, right? The system of equations and its solution, it is going to depend on the properties of the matrix A and the vector F. So this is about converting a system of n first order linear equations into a single matrix form. Okay. So now let me show you the theorems related with this. Okay. So this I have already shown to you. This I have already explained. So this is nothing but block of water predator prey model. This I have already explained. This I have already explained. Fine. So here the system of equations 2. Here, in that case, we are going to assume that they are non-linear. But if you have a linear nth order system, it is going to be written in terms of 3, right? And again, and this is pretty straightforward. You know that if the vector f it is 0, then what happens? The system of equations, it becomes homogeneous. Is it okay with everybody?
Yes, sir.
Fine. Okay. So it is going to be homogeneous. Otherwise, it is non-homogeneous. Okay. So this I have already explained. So right here you can see that the system is homogeneous. Its matrix is of these forms. Right. Simply x prime equal to ax. Okay. Fine. So here I mean system written in matrix notation, and here you can see that the system of equations A, they are, which one is homogeneous and which one is non-homogeneous? Here, can you tell me?
A is homogeneous.
B is
A is homogeneous.
B is also
non-homogeneous.
yeah, B is not homogeneous. A is homogeneous. And now this is important. Basically, what happens if for all the components x1, x2 up to xn, right? You can find some scalar function. You can find some scalar function, say phi1t, phi2t up to phi-nt, right? And if you plug them in the given system of equations, and if they satisfy the given system of equations, so then you say that it constitutes a solution of the given differential equation in the interval of definition. Here they are calling it I. Okay, fine. And of course, like say the entries, they have to be differentiable function. They have to be differentiable function satisfying the system of differential equations. Okay, fine. So now that was about the solution vector. Okay, that was about the solution vector. So now let me take. And again, I mean, the examples that I'm choosing right now, the next time, it may be thinking that it's such a simple example, but I'm going to use that as my model example to explain certain things later on also. So suppose I have this one. 1353. Okay, fine. So now you can check that. You can check that. If I take okay, see now you can check here that if I plug in x1 into this equation, if I plug in x1 into this equation, so then it is going to satisfy the given differential equation. So, for example, what is happening here? What is happening here?
Sir?
Like, yes.
So we can't see the blackboard.
Oh, I have. Sorry, I forgot to. Okay, good. So now you just look at this example. Okay, x prime equal to this. I should write like this. Okay. So now here can I tell that x1 and x2 are solutions of this equation? So basically, what is this? This is simply your dx dt. This is equal to x plus 3y, and this is dy dt equal to 5x plus 3y. Right? So whether that is going to constitute my solution or not. The first one, so that means the first one, the solution will be that x equal to e to the power minus 2t, y equal to minus e to the power minus 2t. Okay, so is it going to constitute a solution? So dx dt is what? Minus 2 e to the power minus 2t, right? So x is e to the power minus 2t, and y is, it is going to be 3 e to the power minus 2t. At least this is satisfied, right? So it is going to be 5 e to the power minus 2t, and this is going to be minus 3 e to the power minus 2t. So this is 2, right? And dy dt, again, this is going to be minus, so this is 2 power minus 2t. So you know that, I mean, x1 satisfies the given differential equation. Is it okay? Fine?
Yes.
Yes, sir.
No? No, is there a no? Then I will explain it. I think this is straightforward, right? Simply I'm plugging in those values. Okay. Now you may be thinking, why? I mean, it is so simple. I'm still plugging in the values, right? So similarly, x2 is solution. Okay. Like here, see here x1 is given by this. I could have simply, I mean, differentiate this. I could have simply differentiated that, and that would have given me minus 2 e to the power 2t, isn't it? Minus 2 e to the power 2t. So my x1 prime, it would have given me minus 2 1 minus e to the power minus 2t. Is it okay? Is it okay?
Yes, sir.
Yes, sir.
Yes. So now look at this. If I take 1 3 5 3 into x1, so x1 was 1 minus 1 e to the power minus 2t, right? Even without working on that, had I done that, what it would have given me? 1 minus 3, that is minus 2. 5 minus 3, that is 2 e to the power minus 2t, right? E to the power minus 2t. Okay, and this is equal to, say this is simply ax1. This is simply ax1. So that would have given me minus 2 1 minus 1 e to the power minus 2t. I'm simply doing some I'm still not making any conclusion. Don't worry about it. Right? Up to this, it is okay?
Yes, sir.
Right? See.
Yes, sir.
Yeah, thank you. So my agenda of doing this simple exercise is that this has given you an idea. This has given you an idea that for system of course, this is a homogeneous system of linear equation of first order. So it has given you an idea that probably the solutions are going to be of the form of some vector, constant vector k into e to the power lambda t. This was my purpose. This was my purpose. Whether you agree or not, but this has given you an idea that it works, isn't it? Is it okay with everybody?
Yes, sir.
Right? It works. It works. Okay. So I will go back to this part later. Okay. So firstly, let me show you some theorems which you are already familiar with, but I still want to give you a quick recap of the theorems. Okay, which are going to be handy for our purpose later on. Okay. Okay, so this we have already verified. So now this is the initial value problem. This is the initial value problem. Yeah. So this is the solution vector. This we have already seen. Sorry. Yeah. So now, if you have to, construct an initial value problem through a system of first order linear equations, so then it could be something like this. It could be something like this. Okay. Here, see again, because I have got the solution vector in the form this, so that is why I am going to consider. Remember, the dependent variable t, it belongs to a closed interval a comma b, right? Okay. So if t naught is a fixed point in that interval, here they are calling the interval as I. So now if t naught is a fixed point in that interval I, so if your x naught is a fixed vector given by this, right? And if the values of the functions x1, x2 up to xn at the point t naught is such that x1 t naught equal to gamma 1, x2 t naught equal to gamma 2, etc. Right? So then you can construct an initial value problem like this. say solve x prime equal to at, because the coefficient matrix A has all the entries as functions of t. That is why they're writing the coefficient matrix as a function of t here, right? So you have to solve this linear system of equations subject to this initial condition. That's it. Okay. So now again, this existence of a unique solution. So if the entries of the matrix AT and FT are functions continuous on a common integral I that contains the point T naught, then the problem that we have defined, there exists a unique solution of the initial problem 7 on that interval. Okay, and you already know the superposition principle. If the vector ft on the right hand side, if it is 0, so then your system of equations, what happens? It reduces to a homogeneous system, right? So what we say is that this is the homogeneous system 5. So if x1, x2 up to xk be a set of solution vectors of the homogeneous system 5, right? So then their linear combination is also a solution. You already know it. Is it okay? Fine. So then again, linear independence and dependence, this also you already know it. So now because the solutions are given in terms of vectors, so here you can see that. And this is also pretty straightforward. You just go through it. So if x1 up to xk are a set of solution vectors of the homogeneous system on an integral I, we say that this is linearly dependent on the integral if there exists constants c1, c2 up to c0 such that the linear combination is equal to 0, right? And if that is not so, so that means if this implies that all the constants c1, c2 up to ck are 0 themselves, and remember here the right hand side is 0, this is a vector. Is it okay with everybody?
Yes, sir.
Right?
Yes.
But when we are going to consider c1, c2 up to ck being 0, they are 0 as scalars. You have to be very careful about that. Okay, fine. And you already know condition for linearly dependent and independent solution. So, do you recall the Wronskian, the definition of Wronskian in terms of solutions of a system of homogeneous first order linear equations? Does it ring a bell? Wronskian? I think you can already see there. Okay, so I am assuming that these are the solution vectors. These are the solution vectors x1, x2 up to xn. Remember, earlier I was talking about only x1, x2 up to xk, where k is assumed to be less than or equal to n. But here I am considering exactly n vectors here. Okay, fine, because I am going to go to linearly independent solutions. Okay, fine. So now the Wronskian definition is simply what you do. You consider whose columns are nothing but the solution vectors. Okay, x1, x2 up to xn, right? And if you take their determinant, it is called the Wronskian of x1, x2 up to xn. That is the difference. Okay. Earlier, what happened? When we consider a single equation, right? We consider a single nth order equation. Okay. And from there, I defined Wronskian in terms of some scalar functions y1, y2 up to yn, right? And the Wronskian was nothing but a determinant whose rows were nothing but the successive derivatives of the linear independent solutions. Is it okay with everybody?
Yes, sir.
Right? So that is simply the difference. Okay. So now, like say, in the previous case, if you recall, I was taking two solutions, x1 and x2, right? And then, like say here, if I want to find out their Wronskian, so I am simply going to put them into this column. So this was x2, if you recall, I walked with that. Okay, this was this was x1 and this was x2. So you see that in the determinant, the columns have come from the solution of the differential equation, and then you can see that it is non-zero here. Okay, and that means that those two solutions are linearly independent. They form a linearly independent set of vectors, right? And such solution or such set of vectors, you know that it is called a fundamental set of solutions. That's it. Okay. So I think I am fine with this. Okay. So hopefully, yeah. And again, there exists a fundamental set of solutions for the homogeneous system 5, and that is nothing but x prime equal to ax on an interval I. And you know that, I mean, if you have a fundamental set, then their linear combination is going to give you the general solution. This is also pretty straightforward. Okay, fine. And then again, if your system of equations is not homogeneous, right? Then you know that what you are going to have, your final solution is going to be nothing but the sum of the complementary function and a particular integral. That is what is going to come in the case of a non-homogeneous system. So this is what it is. If xp is a given solution of the non-homogeneous system on the linear set, right? Then the general solution of the non-homogeneous system on that interval is simply given like this. Okay, right? And then there next time you are going to see that this you can easily verify. Verify that this is a particular solution of the non-homogeneous system. You just simply plug it in here, and then you will see that it is going to satisfy this. Okay, so I think that is all about the recap. That is all about the recap of the theorems. Now, what I'm going to do, I'm going to concentrate on homogeneous linear system with constant coefficients. Homogeneous linear system with constant coefficients. Okay. Okay. Constant coefficients. Okay, fine. Okay. So as before, I am considering this equation. As before, I am considering this system of equation. Okay. So now, in our very first example that we had taken, which is of two homogeneous linear equations, then you saw that it, solution of this form was working. Is it okay? Solution of this form was working there, right? So now the question is, like say, if I consider a system of n homogeneous linear equations, then whether if I take its solution as, something like say k1, k2 up to kn into e to the power lambda t, and this I can write as k e to the power lambda t, right? Whether it acts as a solution or not. If at all, it always acts as a solution, then under what circumstances, right? So that is the fundamental question we are trying to find answer. Okay. So now let us assume that. This is the solution of a given system of differential equations. Okay. So, and of course here remember that this k bar or k, say I'm going to simply call it k. K is a constant vector. Okay. So then if you plug that in here, then what you are going to get, your lambda. This is the left hand side, okay, and the right hand side is simply a this, okay. So this gives you, I can write it as a minus lambda . This is equal to 0, right? Am I okay? Yes?
Yes, sir.
Yes, sir.
Does somebody differ in opinion? The way I have written all the entries there? Yes? Right hand side is also a vector, that is 0 vector. In exam, if you write that as simply scalar, I am going to give you scalar 0. Okay, fine. So, because I always know that this is non-vanishing, so that means I can write this as your A minus lambda I k equal to 0. So far so good, right? See, although I told you that k is a constant vector, I didn't impose any conditions on that. Is it okay with everybody? Till this step, is it okay with everybody?
Yes, sir.
Right? So
Yes, sir.
now what does this I mean tell you? This equation, does it look familiar to you?
If lambda is not an eigenvalue of A, then k bar will be the 0 vector.
Okay, fine. But what other familiarity this has? I mean,
It's
in
a system
relation
of
to the matrix A.
homogeneous linear equation.
No. Forget about now. Okay, for the time being, let us forget about this being coming from a system of differential equation. Let us concentrate on that matrix equation. Okay. So suppose I have a matrix A, right? Suppose I have a matrix A, and from that matrix I get an equation of this type, the very last equation. I have reached an equation of this type. So then, what does it remind you of?
Eigenvalue and
It's a
eigenvector.
system of
This reminds you of eigenvalue and eigenvectors, right? Because you know that if I can find a non-zero vector k such that this relation is satisfied, then your lambda is nothing but an eigenvalue of the matrix A with corresponding eigenvector k. Right? Is it okay with everybody? Right?
Yes, sir.
Yes, sir.
Right? So that
Yes, sir.
means if I can find a solution of this form, or if I find the eigenvalue, say an eigenvalue, say not eigenvalue, say. Forget about all eigenvalues. Let me concentrate on only one eigenvalue. So suppose lambda is an eigenvalue of this matrix, right? And if I can find the corresponding eigenvector k, right? So then k e to the power lambda t, k e to the power lambda t is always going to satisfy the system of homogeneous linear equation x prime equal to ax. Is it clear?
Yes, sir.
Yes?
Yes,
Right?
Yes, sir.
Right? So that is what we are going to do. The theory is developed on this fact. And later on, I'm going to do something else. Then you will see that all the eigenvectors, even when you are in some kind of difficulty, just, using these kind of constant, these kind of concepts, you'll be able to do everything. Okay, fine. So now, let us just do one very small example, and then I'll give you more complicated one. I'm not even talking about the roots, etc. I'm not even talking about the roots, etc. The nature of the roots. Okay. So now, again, since you have already been given an idea, or for that matter, you have been given a concrete idea that if I find out the eigenvalue of the matrix A, right? So then, with the help of the corresponding eigenvector, I'll be able to construct a solution of the matrix equation given by x prime equal to ax. Okay, so that means I definitely will have to concentrate on the eigenvalue. So in order to find that out, what you did, you simply solved the characteristic equation, plugging in the determinant of this matrix to be equal to 0. Is it okay? Fine. And from there you can easily find out the eigenvalues. And once you find out the eigenvalues, eigenvectors are simply very straightforward. Okay. So now let me 2x plus 3y. Very simple example. Okay. So let me try to solve this system of homogeneous equations. So then what is going to happen? This is simply going to be 2, 3, 2, 1. Right, where this is equal to simply x. Okay, fine. So then the characteristic equation is what? 2 minus lambda, 1 minus lambda, minus 6 equal to 0. Okay? Lambda squared minus 3 lambda plus 2 minus 6. So plus 1, right? So right, lambda plus 1 into lambda minus 4 equal to 0. So lambda equal to minus 1, 4. Okay? So now, again, in order to find out the eigenvectors, again, just a minute. I'll come back to this again. I want to get back to here, this one. Sorry. Let me try to get back to this. Okay. See, when I plugged in, x equal to k e to the power lambda t, it eventually led me to this. Okay. It eventually led me to this. And somebody was also telling me when I asked one question about the relation between, k being 0, right? So now you answer me one question, right? Like say, here, obviously, k could have been the 0 vector. K could have been the 0 vector, isn't it? Right?
Yes, sir.
K could have been 0 vector. And what I told you, that I wrote in the concept, I told you that, okay, forget about this being coming from, a system of differential equations. No, we cannot forget that. We simply cannot forget that. It has come from a system of differential equations, right? So let me try try to stick to that. It has come from the set of system of differential equations. So now, what is going to happen? Can you tell me when k is equal to 0, the 0 vector, then what happens?
Then lambda can't be the eigenvalue of A.
No, even I mean, forget about lambda. Can you think about the eventual solution of the differential equation?
That will be zero solution.
That will be zero solution. That is where the point lies. Okay, that is where the clue lies. So, but we are not seeking trivial solutions, isn't it? Because we already know that the trivial solution is always a solution of a system of homogeneous equations. For that matter, any homogeneous equation, right? Is it okay? Are you getting my point?
Yes, sir.
Yes, sir.
Yes, sir.
Right? See, I am seeking solutions like this. So if now this is what? This is something like, I have something like this. I have something like this. This is 0, right? I have something like bx equal to 0, right? So if I have this, and if I am seeking non-zero solution, because I mean, if B is invertible, definitely you are going to get a unique solution. That solution is going to be simply the trivial solution. Is it okay with everybody?
Yes.
Right? So that is why, in order to get non-trivial solution, so this determinant of this matrix must be equal to 0. Is it okay?
Yes, sir.
Yes,
Fine.
sir.
Fine. The determinant of this matrix must be equal to 0. So that is where this comes from. Yeah. Because we cannot think independently, right? See, it has to come from the set of given differential equations. Is it okay? Now it is clear, right? Why we go for eigenvalues and eigenvectors. Okay? And then the remaining stuff you already know. Okay, fine. So now let me get back to that. Let me get back to that. Okay. In this particular case, A was given by 1, 3, 5, 3. Okay, fine. So then your if A minus 1I. So this is simply what? 2, 3. 2, 3, no 2, 3. So A plus I, right? Yeah. And it will be what?
So the matrix was different.
Matrix was different. Oh no. It is 2, 3, 2, 1. Sorry.
Yes.
2, 3, 2, 1, right? So 2 plus 1, this is 3, 3. 2, 1 plus 1, 2, right? So you know that through elementary transformations, this can be converted into this, right? Isn't it? Say, firstly, what you do R1 is 1 by 3 R1, R2 is 1 by 2 R2, right? So then simply after this, you simply do R2 is R2 minus R1. Is it okay with everybody?
Yes, sir.
Yes, sir.
Right?
Yes, sir.
Okay. So finally, you know what is the corresponding eigenvector?
1 minus 1.
1 minus 1, simplest. 1 minus 1 or minus 1. Okay. So that means the first one, K1 is 1 minus 1. Okay. So now A minus 4I, this is going to be 2 minus 4, minus 2, 3. Then 2, 1 minus 4. Okay. Right? Again, I mean, you know that this is going to be equivalent to 0, 0. You know how you can obtain. Simply R2 is R2 plus R1. Right? So what could be K2? Just look at this. 2 into 3 plus this into 3. It is already minus, right? 3 into 2. That is going to give you 0. Is it okay with everybody?
Yes, sir.
Right? So 3, 2. Fine. So that means your my final solution is going to be something like this: C1 x1 plus C2 x2. Right? So here x1 is k1 e to the power lambda 1t. So this is k1 1 minus 1 e to the power minus t plus C2 3 2 e to the power 4t. Is it okay? Fine? Yes? Okay. Are you finding it too easy? Should I skip it? I'm not going to skip it because I say I have started with a very easy one. Things are going to be more complicated later. Okay. So and I need some building block. I need some building block. Okay, fine. How much time do I have? Oh, but anyway. Now, okay. So now let us consider the case. Let us consider the case, maybe case one, when the roots of the characteristic equation are distinct. Okay, so you know, I mean, see, the characteristic equation is nothing but this one. You already know, right? You already know this. Okay, this is 0 or 0 bar.
0.
0.
Are you sure? Are you sure?
Yes, sir. Because it is determinant.
This scalar, this is going to be determined, right? Okay. See, in this case, you have already seen an evidence of this one. So, this case, I mean, the previous example that I worked out, that is related to this one, right? So, then what happened here? You could definitely see that the eigenvectors, these two eigenvectors, right? And for that matter, what happened? Even just let me give you an idea. Say, okay, I'll come to that later on when the roots are not distinct. Okay, so if you look at x1 and x2, you can see that one is not the scalar multiple of the other, right? So that means they are linearly independent. Or what you can do, even you can try to find out the Wronskian also. You'll see that the Wronskian will come out to be non-zero there. Because it is always going to be some e to the power something. It is going to be in terms of some exponential function. And since exponential function is non-zero, I mean the Wronskian is non-zero. Okay. So when the roots are of the characteristic equation are distinct, then what happens? You are always going to get your a set of n linearly independent set of vectors, okay, as solution. Okay, probably from linear algebra also you are aware of that. Is it okay with everybody? Fine.
Yes, sir.
Yes. So now let us see when it is not distinct. Case 2. Just a minute. Roots are not only distinct; these are real and distinct. Real and distinct, because I'll have to come to complex also. No? Okay. And then here, when and still I am in real, complex I will come later. When it has real roots, characteristic equation has real roots, when some of the roots are repeated. Some of the roots are repeated. So, do you know what you do then? Right? So that brings me to the idea. You already know it. So that means the characteristic roots, some of the characteristic roots, they say if some of the roots are repeated, then say suppose like say I have a characteristic root lambda 1 which is repeated. So that means it must be a characteristic root of some multiplicity which is greater than 1. Is it okay?
Yes, sir.
Yes, sir.
Fine?
Yes, sir.
Fine. So that means say suppose this lambda 1 is a characteristic root of say multiplicity m. So that means your lambda minus lambda 1 to the power m is a factor of your characteristic equation a minus lambda I, right? This is a factor of your characteristic equation. So basically the left hand side of the characteristic equation. Okay? This is a factor, but lambda minus lambda 1 to the power n plus 1 is not a factor. Is it okay? Fine? Is it okay?
Yes, sir.
Right? Okay. So now what may happen? What may happen when you have a root of multiplicity n? Again, some cases may happen. In tomorrow's class, I am going to discuss in detail, but let me mention it. So again, 2 separate cases can happen. That, like say, corresponding to this lambda 1, you will be able to find. I mean, m linearly independent eigenvectors. Okay, it may so happen. Although I mean it looks impossible, but it may so happen. I'll give you an example. Okay, and it may so happen that it has only one eigenvector. Okay, fine. So then what are you going to do? Because ultimately we are going to seek a fundamental set. Okay, so in that case, what you are going to do, I am going to describe in tomorrow's class. Okay, and did you guys do a follow-up of that Lysender's equation? I mean, yesterday that I taught. Did you actually check the pages of CMOS? Anybody? No. Okay. No? You have so many other things to study, right? In a day, how many classes are you attending? On average. Yesterday, how many classes did you attend? I mean, all the people. Only one class or multiple classes?
Sir, on an average, 2 classes.
2 classes. Okay. But that shouldn't be too much of a burden, right? Isn't it? See, if you don't do the follow-up, instantly, then later on you are going to forget. And again, I'm going to ask you some questions on the part which I have left as a homework in exam, then you'll be in trouble. So I'm warning you guys. So be careful about it. Whatever I tell you to do at home, do it on the same day. Okay? So with that note, I'm going to leave you today. So I'm going to see you tomorrow again.